Welcome to this scientific lecture on one of the most fascinating phenomena in nanoscale chemistry, the soluble-insoluble switch paradox. Imagine you have a chemical that absolutely refuses to dissolve in water or oil when you put it in a beaker. You stir it, you heat it, but it remains stubbornly insoluble. Now, take that same chemical and place it inside a tiny microdroplet just 10 micrometers across. Suddenly, it dissolves completely. This is the paradox we're going to explore today. On the left, we have a bulk beaker where yellow particles, representing our chemical, remain clumped and undissolved. On the right, inside a tiny microdroplet, those same particles are uniformly distributed and fully dissolved. Same chemical, same solvent, but drastically different behavior. The question we must answer is, why does size matter so dramatically? The answer lies in the concept of curvature-modified chemical potentials. Before we dive into the curvature effects, let's review what chemical potential actually means. Chemical potential is essentially the driving force for molecules to move from one phase to another. It's like a measure of how much a molecule wants to escape from where it is. The chemical potential mu equals mu naught plus RT natural log of A. Here, mu naught is the standard chemical potential, R is the gas constant, T is temperature, and A is the activity of the species. In large bulk systems like a beaker, this standard equation works perfectly. The chemical potential depends only on concentration and temperature. However, when we have highly curved interfaces, like the surface of a tiny droplet, an additional term appears that modifies the entire equilibrium. The key to understanding this paradox is the Laplace pressure. This is an extra pressure that exists inside curved interfaces. The Laplace pressure delta P equals gamma times the sum of 1 over R1 plus 1 over R2. Here, gamma is the surface tension, and R1 and R2 are the principal radii of curvature. For a spherical droplet, both radii of curvature are equal to the droplet radius r, so the equation becomes much simpler. Delta P equals 2 gamma divided by r. This is the excess pressure inside a spherical droplet compared to the outside. You might be wondering, what does pressure have to do with solubility? The answer is that pressure affects chemical potential. The chemical potential inside the droplet equals the bulk chemical potential plus Vm times delta P. Here, Vm is the molar volume of the substance. Substituting our expression for Laplace pressure, we get mu droplet equals mu bulk plus 2 gamma Vm divided by r. Notice that this correction term has r in the denominator. As the droplet gets smaller, this term gets much larger. This is the heart of the paradox. Let's make this concrete with real numbers. Consider a water droplet with typical organic molecules. For water at 25 degrees Celsius, the surface tension gamma is approximately 0.072 newtons per meter. Gamma equals 0.072 newtons per meter. The molar volume for a typical organic molecule is about 100 cubic centimeters per mole, which equals 10 to the negative 4 cubic meters per mole. Let's first consider a relatively large droplet with radius 1 millimeter, which is 10 to the negative 3 meters. Delta mu equals 2 times 0.07, 2 times 10 to the negative 4, divided by 10 to the negative 3, which equals 0.0144 joules per mole. At room temperature, RT is approximately 2,500 joules per mole, so 0.0144 is completely negligible. The curvature effect doesn't matter at all for millimetre-sized droplets. Now let's consider a microdroplet with radius 10 micrometers, which is 10 to the negative 5 meters. Delta mu now equals 1.44 joules per mole. This is still relatively small, but it's becoming significant. Now the truly dramatic case, a nanodroplet with radius 100 nanometers, which is 10 to the negative 7 meters. Delta mu now equals 144 joules per mole. This is about 6% of the thermal energy, which is definitely significant. And finally, for a very tiny nanodroplet with radius 10 nanometers, which is 10 to the negative 8 meters. Delta mu is now 1440 joules per mole. This is more than half of the thermal energy. At this scale, the curvature completely dominates the thermodynamics. This graph shows how the chemical potential change increases dramatically as droplet size decreases. It's an inverse relationship, so tiny changes in radius at the nanoscale produce enormous changes in chemical potential. Let me give you a helpful analogy. Think of the chemical as a stubborn ingredient that refuses to mix in a large bowl. In a large beaker, molecules have essentially infinite space to explore and many ways to avoid dissolving. They can aggregate, form crystals, or simply sit at the bottom. But in a tiny droplet, the high Laplace pressure creates a kind of molecular claustrophobia. The molecules are squeezed together so tightly that they have no choice but to interact intimately with the solvent. It's like putting two people who don't get along in a tiny elevator. They have to deal with each other. The curvature acts like a molecular matchmaker, forcing interactions that wouldn't happen in bulk solution. This changes the energetics of dissolution completely. Now let's be more quantitative about how solubility changes with droplet size. The natural log of S droplet divided by S bulk equals 2 gamma Vm divided by RTR. This equation tells us exactly how much more soluble a substance becomes in a small droplet. Here, S represents solubility. S droplet is the solubility inside the curved droplet, and S bulk is the normal solubility in flat bulk solution. Let's calculate the solubility enhancement for our 10 nanometer droplet at room temperature. The natural log of S droplet over S bulk equals 1440 divided by 2500, which is 0.576. Taking the exponential, S droplet over S bulk equals e to the 0.576, which is approximately 1.78. This means the solubility increases by 78%. A chemical that barely dissolves in bulk can have almost double the solubility in a tiny nanodroplet. And remember, this is an exponential relationship. For even smaller droplets, the enhancement can be factors of 10 or even 100. You might be asking yourself, if this effect is so dramatic, why don't we notice it all the time in everyday life? The answer is that most droplets we encounter in daily life are much larger than the critical size. Raindrops, spray droplets, even fog droplets are typically tens to hundreds of micrometers in size. At 10 micrometers, the solubility enhancement is less than 1%. It's there, but it's too small to notice without precise measurements. Creating and maintaining stable nanodroplets requires specialized techniques like microfluidics, ultrasonication, or careful emulsification with surfactants. Nature doesn't commonly produce such small, stable droplets. Another important question: does this work for oil droplets in water as well as water droplets in oil? The answer is yes, absolutely. The key parameter is the interfacial tension between the two phases. Oil-water interfaces typically have tensions of 20 to 50 millinewtons per meter. For a typical oil-water interface, gamma is approximately 0.035 newtons per meter, which is about half that of pure water. This means the curvature effect will be somewhat smaller for oil droplets, but at the nanoscale, it's still very significant. Now let's discuss why this matters beyond pure scientific curiosity. This phenomenon has profound, practical implications. First, drug delivery. Many pharmaceutical compounds are hydrophobic and have poor solubility. By formulating them in nanoemulsions, we can dramatically increase their effective solubility and bioavailability. Second, chemical reactions. Reactions that are too slow or don't proceed at all in bulk solution can occur rapidly in microdroplets. This is the basis of microdroplet chemistry, a rapidly growing field. Third, atmospheric chemistry. Tiny aerosol droplets in the atmosphere can dissolve and react with chemicals that wouldn't normally dissolve in bulk water. This affects cloud formation, pollution chemistry, and climate. Fourth, material synthesis. Controlled precipitation and crystallization in nanodroplets allows for the creation of nanoparticles with precise sizes and properties. These four circles represent the major application areas where the soluble-insoluble switch paradox plays a critical role. All are connected by the fundamental principle of curvature-enhanced solubility. One important practical aspect we haven't discussed yet is the role of surfactants in stabilizing these tiny droplets. Surfactants are molecules with both hydrophilic and hydrophobic parts. When they adsorb at an interface, they lower the interfacial tension gamma. Gamma with surfactant is less than gamma pure. This reduces the magnitude of the Laplace pressure. You might think this weakens the solubility enhancement, and it does somewhat. However, surfactants also stabilize the droplets against coalescence. allowing them to exist at much smaller sizes for longer times. With the right surfactants, we can create microemulsions with droplet sizes below 50 nanometers. These are thermodynamically stable and can persist indefinitely. For those wanting to go deeper, there's a related phenomenon called the Kelvin effect, which describes how vapor pressure changes over curved surfaces. The natural log of P over P naught equals 2 gamma Vm divided by RTR. Notice this has exactly the same form as our solubility equation. The Kelvin equation tells us that small droplets have higher vapor pressures than flat surfaces. This means they evaporate more readily. This is one reason why very small droplets are difficult to form and maintain. They want to evaporate or condense onto larger droplets through a process called Ostwald ripening. An astute question you might ask is, does this apply to solid nanoparticles as well as liquid droplets? Yes, absolutely. For solid nanoparticles, this is called the Gibbs-Thomson effect. Small crystals are more soluble than large crystals of the same material. The equation is similar. Natural log of S nano over S bulk equals 4 gamma Vm divided by RTD, where d is the particle diameter. This explains why nanoparticles of the same compound dissolve much faster than bulk powders. It's not just surface area, it's also enhanced solubility. Let's step back and think about this from a fundamental thermodynamic perspective. Any system at equilibrium minimizes its total free energy. For a droplet, this includes both volume free energy and surface free energy. The total free energy, G, equals G volume plus G surface. The surface free energy equals 4 pi r squared gamma for a sphere. As the radius decreases, the surface area to volume ratio increases. Surface energy, which is unfavorable, becomes increasingly important and eventually dominates the thermodynamics. This surface energy contribution modifies all thermodynamic properties, including chemical potential, solubility, vapor pressure, and melting point. The smaller the system, the more dominant these surface effects become. You might wonder, is this just theory, or has it been experimentally verified? First, enhanced dissolution has been directly measured in spray droplets. Compounds that are insoluble in bulk water dissolve readily in micrometre-sized spray droplets. Second, chemical reactions occur thousands of times faster in microdroplets than in bulk solution. This has been documented in hundreds of studies. Third, the related Gibbs-Thomson effect has been confirmed by measuring melting point depression in metal nanoparticles. Gold nanoparticles smaller than 5 nanometers melt at temperatures hundreds of degrees below bulk gold. Fourth, the size-dependent solubility of nanocrystals has been measured using techniques like dynamic light scattering and spectroscopy. Before we conclude, we should acknowledge that the simple model we've discussed has limitations. First, we assumed surface tension is constant with curvature. In reality, for very small droplets below a few nanometers, the surface tension itself may change. Second, we used macroscopic thermodynamics. When droplets contain only hundreds of molecules, molecular-level statistical mechanics becomes necessary. Third, we ignored electrostatic effects. Charged droplets or ions can introduce additional terms that modify the chemical potential. Despite these limitations, the curvature model we discussed works remarkably well for droplets larger than about 2 nanometers, and gives good, semi-quantitative predictions even for smaller systems. Let's summarize the key concepts from this lecture. First, curved interfaces create an excess pressure inside droplets due to surface tension. This is the Laplace pressure. Second, this pressure modifies the chemical potential of dissolved species, making them more or less stable depending on the sign of the curvature. Third, the effect scales inversely with droplet radius. Cutting the radius in half doubles the effect. This makes nanoscale droplets behave very differently from bulk solutions. Fourth, this effect can change solubility by factors of 2, 10, or even more in sufficiently small droplets. A completely insoluble compound in bulk can become highly soluble at the nanoscale. Fifth, this phenomenon has practical applications in drug delivery, chemical synthesis, atmospheric science, and materials engineering. The fundamental equation to remember is delta mu equals 2 gamma Vm divided by R. This single equation captures the essence of the soluble-insoluble switch paradox. Finally, let's consider what this tells us about the nature of matter at small scales. At the nanoscale, matter doesn't behave according to our bulk intuitions. properties we consider fundamental, like solubility, melting point, and reactivity, become size-dependent. Surface effects begin to dominate over volume effects. Every atom or molecule in a 2-nanometer particle is near the surface, experiencing different forces than in bulk. This is why nanotechnology represents a true paradigm shift, not just miniaturization. We're not just making things smaller. We're entering a regime where different physics applies. The stubborn ingredient that suddenly agrees to mix in a tiny cup is showing us that nature follows different rules when confined to nanoscale dimensions. Understanding these rules opens up new possibilities for science and technology. This flow diagram captures the causal chain. Curvature leads to pressure, pressure modifies chemical potential, and modified chemical potential causes the solubility switch. Each era represents a fundamental physical principle. Thank you for joining me on this deep dive into one of the most elegant and consequential phenomena in physical chemistry. The next time you see a fine mist or spray, remember that those tiny droplets are obeying very different thermodynamic rules than the bulk liquid they came from.